Hello guys, we'll be doing this February March 2022 exam paper. This is paper 2 and this is paper 2 and it is February March 2022. The latest exam just happened in the India, the March 2022 paper. So let's get started with the first question. The first question says the figure 1.1 shows how first ionization energies vary across period 2. Do remember that the concept here is they're saying across the period, not down the group, across the period. You can check from the periodic table, right? So it's across the period. So I would like to tell you one thing, that have a periodic table in front of you, and from these 2022 exam papers, these 2 points are very important points. That the periodic table will be printed inside the question paper, and the important values, constant and standards are printed at the back of the paper. So you won't be given with data booklet, rather you will be given with everything you need to know in that question, or either that the periodic table will be given at the end and the constant important values will be given at the end of the paper. I will show you when it comes. It is inside this paper. Okay, so this is a perfect example for the preparation of the onward exams from May June series 2022. Okay, so he has shown us some ionization energy variation across the period 2. Now he's saying that construct an equation to represent the first ionization energy of oxygen. Okay, first ionization energy of the oxygen. We're going to put the state symbols too, and how we're going to write it, that oxygen, which is in gaseous form, 1 mole of that is forming 1 mole of positive ion, or you can say cation, in gaseous form, and 1 electron is eliminated. Now why this is +1, why not anything else? Because the first ionization energy, whatever the number of ionization energy, that's basically the charge on the cation on the right hand side. So do remember that. So let me just define the first ionization energy. It is the amount of energy that is needed to remove 1 mole of electrons from 1 mole of atoms of an element in gaseous state to form 1 mole of gaseous cation. So do remember that. It's 3-mark definition. Okay. Now next part. State and explain the general trend of first ionization energy across the period 2. Very simple question. First of all, there's 1 mark for the stating the trend, and the 2 marks are for the explaining the trend. So we know that the ionization energy increases across the period, right? We know that ionization energy increases across the period. Now what are the reasons for that across the period, right? Now what's the reason for this across the period 2, or whatever the period is, 3 or whatever, it increases across the period. Okay, now what is the explanation for this? We know I won't be writing everything like I'm a student. I will just be writing the key concept and you can write your answers from there, right? So the main thing here you gotta write is that the nuclear charge increases across the period, right? The nuclear charge increases across the period. Nuclear charge increases, and guys, we all know that distance between nucleus and outer electrons remains reasonably constant. Electrons are being added to the same shell, to the same quantum shell, to the same, right, to the same shell. So that's why, by same shell I mean the valence shell, which is the quantum number, right? The quantum shell, not the subshell. So yeah, so nuclear charge increases, distance between nucleus and outer electron remains the same, reasonably constant. The shielding effect remains constant. Shielding effect is constant. Shielding effect is constant. Okay, now what happens is these two factors cause the nuclear attraction to increase. By what do I mean by nuclear attraction? Nuclear attraction is the attraction between the nucleus and the outer electrons that increases. So which means that more energy is needed to overcome this increased nuclear attraction. So that's why ionization energy increases across the period. I hope this is 3 marks. Next part. Explain why ionization energy A does not allow the general trend does not follow the general trend in first ionization energy. Okay, where's element? Where's A? Okay, this is about oxygen. So if you look at the periodic table, the oxygen is, let me just look at the periodic table. Oxygen is, yeah, atomic number is 8. Oxygen is atomic number 8. So which implies that it is 1s2, 2s2, and 2p4, right? 2p4. So we got to write that it is due to spin pair repulsion. Spin pair repulsion of the electrons, right? What is spin pair repulsion? It is like electrons in the same orbital repel each other more than electrons in different orbitals. So the pair of electrons, the extra repulsion created between the extra repulsion created between the pair of electrons makes it easier to knock out an electron, to remove an electron from the 2p of the oxygen, right? So what we're going to write is the extra repulsion between the second pair of electrons, between the second pair of between the second pair of electrons in 2p of oxygen makes it easier to remove an electron, makes it easier to remove an electron, right? To remove an electron. So why is easy to remove an electron? Because it's extra repulsion, and that extra repulsion outweighs the increased nuclear charge. You can also write that outweighs increased, I mean, it all makes sense, right? Outweighs increased nuclear charge, right? So yeah, this is done here. 2 marks, right? Very easy, right? So also do remember the stability of the subshells, that completely filled subshells are more stable than half filled subshells, which are more stable than partially filled subshells. So do remember that. Okay, next part. Now we have to write reduce full electron configuration of element E and explain your answer. So first of all, he's told us period 3, right, of the periodic table. Now, whenever he's asking us full electronic configuration, we do know that it's in period 3, but we don't know which group is it in the period 3, right? So, to find a group number, what we're going to do is look for the large jumps in the ionization energy. I can see a pretty large jump between this. So, whatever the jump is between the two ionization energies, the smaller one of them is the group number. This is the group number. It is in the group 13 of the periodic table in the period 3. Now, why is that? Because there's a large jump between third and fourth ionization energy, which implies that there are 3 electrons in the valence shell. Hence, it must be in group 13 of the periodic table. So you're going to write. So what is in group 13 of the periodic table and period 3? Let me just write it. It's aluminium, right? I looked it from the periodic table, and you should do the same thing. Aluminium is in period 3, group 13. So we're going to write the electronic configuration: 1s2, 2s2, 2p6, 3s2, and 3p1. Now, whatever the explanation I have told you, you're just going to write it inside. There's a large gap between, don't write between like this, write the proper between, right? Between the third and fourth ionization energy. Right? Ionization energy complete. I'm just writing it to save time. Ionization energy. Hence, there are 3 electrons in the valence shell. That's why it is in group 13 of the periodic table. Group 13 of the periodic table and period 3. So it implies that the element is aluminium by using periodic table. So this was 9-mark question. It is done here. Next part. We'll be going through this inorganic part very quickly. Okay, so the period 3 oxides are shown. Okay, we know that. Sodium reacts with oxygen to form sodium oxide. Very easy. It is a reducing agent. Sodium is a reducing agent. What is a reducing agent? A reducing agent is a species. It's a species that reduces a substance by donating it electrons. Species. It is a species that reduces a substance or another substance by donating electrons, right? It gives away electrons. So by giving away electrons, it loses electrons. It itself gets oxidized, but it reduces the other substance, right? So do remember that. Equation for the reaction of Na2O into water, very easy. Sodium hydroxide will form Na2O plus H2O will form NaOH, and you got to balance that. I think there must be a 2 here, and that's it. The equation is balanced, right? So you have to remember these equations. These have no explanation. You got to remember them. You got to memorize them. It's an amphoteric oxide. Al2O3 is an amphoteric oxide, and it is found in bauxite. What is meant by amphoteric? A substance that has tendency to react with both acid and bases. Substance that has tendency or ability that has tendency or ability to react with both acids and bases, right? Okay, nice. Next part. Al2O3 is purified from bauxite in several steps. Okay. The first step involves heating Al2O3 with an excess NaOH aqueous. A colorless solution forms. Okay. You also have to remember that it is that sodium aluminate forms in this reaction. We have to add water to in this step, right? Al2O3 plus NaOH plus water. This is a rule. We have to add the water in this reaction, and sodium aluminate will form NaAlOH4, right? So we gotta balance that. The two aluminiums on here, so I should put two here, and then it will be eight already, two here, so three here, right? Do remember this equation that whenever aluminium oxide reacts with NaOH, we get this. Whenever it reacts with HCl, we get AlCl3. Okay, it may ask that too. It has asked us several times. Okay, next one. Al2O3 is used as a catalyst in dehydration of alcohols. The effect of using Al2O3 as a catalyst in dehydration of alcohol, use the Boltzmann distribution curve to explain. Okay, so we know Boltzmann distribution curve had number of molecules in the y-axis and the energies on the x-axis. Okay, we're gonna use this diagram and we're going to use this page to obtain this easy 3 marks. So how we're gonna do that? For example, let's label it EA without catalyst. EA without catalyst, right? And let's say this is EA with catalyst. Reduced, right? Catalyst reduces activation energy, right? So you get 1 mark for this. Now you gotta explain that. So you gotta write that catalyst increases rate of reaction, catalyst increases rate of reaction. Don't write rate of reaction like this. I'm repeating it. Write the full form, just writing it to save time. Rate of reaction by lowering activation energy. So now more particles have, or molecules, because here is molecules, more molecules have energy greater or equal to the activation energy. Hence frequency of successive collisions increase because energy increases. Frequency of successive collisions increases, right? Because the energy has increased. So just notice here, look, before there were these many molecules having enough energy to react, right? Now this much additional molecules have energy because activation energy has been decreased by the catalyst, right? I hope you get the point. Increase, I don't even know this fair. Increase, right? Sorry, increase. Okay, next part. P4O6 is a white solid, has melting point of 24, has a melting point of 24 degrees Celsius, very low melting point, right? The oxide has very low melting point. Reacts with water to form H3PO3 hydrolysis reaction. Very simple, right? Deduce the type of structure and bonding shown by the explain your answers. Okay. The type of structure is what? What's the type of structure? It's a simple molecular structure, right? Simple molecular structure. Now, why do I know that? Because low melting point of the oxide. Look, you can write that low melting point. Okay, write in the full form. Okay, and what's the bonding? It's covalent bonding. Why do I know that? How do I know that? Covalent bonding. How do I know that? Hydrolyzed when added to water. Hydrolyzed when added to water, right? Do remember that, added to water. Okay, next part. Determine the oxidation number of P in H3PO3. Very easy, right? H3PO3, so there are 3 hydrogen. Hydrogen is +1, and phosphorus we have to determine, and oxygen is 3, and the oxygen oxidation state is -2. This whole compound is 0, right? So I forgot to write 1 here. Okay, so this is +3 plus P -6 is equal to 0. So P -3 is equal to 0, and P is actually +3. Okay, I'm writing it so that you all guys understand. Okay, +3. So this is how you do this, right? When P4O6 is reheated with oxygen, it forms P4O10, which is a solid. Okay, so basically burning it, kind of, right? So What does this indicate? The delta HR, the enthalpy of reaction is exo. Negative sign indicates exothermic energy is released to the surrounding, right? The enthalpy change of formation. The enthalpy change of formation is given of P4O10 product is given. Calculate the enthalpy change of formation of the reactant, which is this, right? Very easy. We use a formula. The formula is the enthalpy change of reaction is equal to the sum of enthalpy change of products, of products minus enthalpy change of reactants minus the change in enthalpy change of reactants, right? Okay, now we just put in the values. Delta H is minus 1372. The product formation P4O10 is given, which is minus 3012, and minus this P4O6, which we have to find. So for P4O6, what we get is actually this will go there to make positive. This will come here, and so minus 3012 plus 1372, we get an answer of minus 1640 kilojoule per mole. You got to write the minus sign, or you get no marks. 1640. This is a good formula. Okay, very easy, right? Write an equation for the reaction of P4O10 with water. Phosphoric acid will form. P4O10 plus H2O makes phosphoric acid H3PO4. You can balance it. There are 4 phosphorus on the left hand side, so 4 here, and now there are 12 hydrogens, so 6 here, right? Oxygen will be balanced, or should be balanced. There's 16 oxygens, right? SO2 and SO3 are found in the atmosphere. The oxidation of SO2 to SO3 in the atmosphere is catalyzed by NO2. Okay, you should know that yourself too. The first step of catalytic oxidation is shown. Okay, this is the equation 1, and this is the catalytic reaction that is shown. Construct an equation to show how NO2 is regenerated in the catalytic oxidation. Okay, NO2 was the catalyst, right? So NO2 got reduced, formed NO, but for it to be catalyst, it should remain unchanged, right? It is regenerated in the air. How? This NO reacts with further air, oxygen in the air to form NO2 again. Very easy, right? You can balance that, put half here. We can multiply the whole equation by 2. Both equations are absolutely correct. One is not more correct than the other. Okay, both are absolutely correct. Next part. NO2 also reacts with unburned hydrocarbon to form photochemical smoke. State the product of this reaction that contributes to the photochemical smoke. Okay, now before they used to ask, this is for new syllabus, 2022 syllabus. Okay, it is in the nitrogen and sulfur chapter. They added this. We should only know the name of the compound. That's it. Okay. So now, before they ask like what is like the photochemical smoke, we used to say nitrogen dioxide, but actually nitrogen dioxide reacts with some unburned hydrocarbons to form the photochemical smoke. So the actual compound name of the photochemical smoke, the actual compound that contributes to the photochemical smoke, is the product of the reaction of NO2 and the unburned hydrocarbon. The name is peroxy acetyl nitrate, or you can also write pan nitrate. They will never ask you the structure of this. You can just need to remember the name, the product of the photochemical smoke. But if I try to figure out the name, this is peroxy. Peroxy is, something related to the peroxide ion. Peroxide. Acetyl is always what? CH3, CO, and anything can be here. This is the acetyl group, acetic acid, we just add an OH here. This is an acetic acid. So this is the acetyl group, right? The acetyl group. Nitrate is, we know, NO3 minus 1 minus, right? NO3 minus. So by combining these, we can make a structure of pan CH3 CO. We can add an oxygen here for this one, right? For this one we can add an oxygen for peroxide, and then an oxygen for the nitrate, and nitrogen is here, and then double bond and a single bond, and there's a minus. So nitrate, this is nitrate, right? Nitrate. This is peroxide, and this is the acetyl group. You should not be knowing this structure. You should only be knowing this knowledge that photochemical smoke, the product in it is peroxyacetyl nitrate, right? Okay, next part. Oh, what on earth is this graph? Okay, it shows the temperature, how the temperature of atmosphere varies with the height from the ground. This is the height from the ground, and this is the temperature, how the temperature varies. The equilibrium in reaction one has this enthalpy change of reaction, which indicates that it is again exothermic. It suggests how the position of equilibrium differs at height of 20 and compared to the height of 50. Explain your answer. Okay, at height of 20, what's the temperature? almost minus 55 maybe, right? And at 50, what 50 is something very higher than that. It is, I think, 0. Yeah, 50 it is 0, and here it is minus 55 maybe, right? So when temperature increase and the forward reaction is exothermic, by the way, it's talking about this reaction, equation 1, right? Okay, forward reaction is exo. So when the forward reaction is exo, we increase the temperature, equilibrium will shift to the right, will equilibrium shifts to the right when the forward reaction is exothermic, right? And we increase the temperature. So it's gonna write at height is equal to 20 km, right? Position of equilibrium shift to the right, position of equilibrium. This higher there is higher temperature. Wait, no. When temperature increases, the position of equilibrium shifts to the left, actually, right? Because when the forward reaction is exothermic, when the forward suppose this reaction is exothermic, we increase the temperature. This is already releasing energy, and we increase the temperature. According to Lee-Chatelier's principle, the position of equilibrium will shift in such a way to decrease the oppose the increase in temperature. So it will shift towards the endothermic side, which is the backward reaction. So increasing the temperature will shift the position of equilibrium to the left. So but at 20 the temperature is very low as compared to temperature at 50, right? Minus 55 is lower than 0 degree, right? So position of equilibrium, when we lower the temperature and the forward reaction is exo, then the equilibrium will shift to the right. So that's what we're going to write here. At 20, where the temperature is low, we're going to write the position of equilibrium. The position of equilibrium will shift. It will shift to the right. Why? Because forward reaction is exothermic. Forward reaction is exothermic. And low temperature will shift the position of equilibrium. Low temperature will shift the position of equilibrium to the right. Shift position of equilibrium to right. You can actually use some of this space if you want to, but not too much. Don't go beyond this pathway, right? You can also write about you have to write actually about the 50 km too. That at 50 km the temperature is higher, so the position of equilibrium is shifted to the left because the forward reaction is exothermic. This is a must mention point. This was very 16 mark question. We've done it quickly. Next part. Hydrogen halide, HCl, HBr, and HI are all colorless gases at room temperature. Hydrogen halides can be formed by reacting halogen with the hydrogen. Describe, and 1 point for 1 mark for describing and 1 mark for explaining your statement, that relative reactivity of halogen down the group when they react with hydrogen. Okay, this is easy. That the reactivity of the halogen towards the hydrogen decreases. It decreases down the group. The reactivity of the halogen towards the hydrogen decreases down the group. Now what is the reason for that? The reason for that is electronegativity decreases down the group. Electronegativity decreases down the group. Decreases down the group. Now guys, look, what does this statement mean? This is very important. This statement actually means that down the group in the halogens, we know that oxidation power decreases, right? Power decreases. So oxidation power, these are oxidizing agents, right? When their oxidizing power decreases down the group, we know that when oxidizing substance, it oxidizes another substance, itself it gets reduced. And the addition of hydrogen is what? It is reduction, right? Itself, when its ability to get oxidized decreases, means that it is not easily reduced. The substance, the oxidizing agent itself gets reduced, right? So when the ability to get reduced decreases, it means that its reaction with the reactivity of the halogen towards the hydrogen will also decrease. Try to understand it. It is a very simple concept. Write an equation for reaction 1. SiCl4 undergoing hydrolysis is very easy. SiCl4 plus H2O. It will form SiO2 plus HCl. You got to balance that. 4 HCl here, so 4 here and 2 here. This is the Phoenix balance. You have to remember this is the hydrolysis reaction, right? Next part. Next part is saying in reaction 2, NaCl reacts with H2SO4 to form HCl, and this is sodium thiosulfate, NaHSO4. When NaBr reacts with concentrated H2SO4, the products include Br2 and SO2, right? Identify the types of reaction that occur in each case by completing table 1. Explain the differences in these reactions. So 1 mark for the explanation, 1 mark for each stating the type of the reaction. So for NaCl and H2SO4, these reactions are a typical acid base reaction. Now for NaBr and H2SO4, it is an acid base reaction. It is to some extent some acid-base reaction, and to some extent it is a redox reaction. And if you talk about NaI redox, and if you talk about NaI and H2SO4, it is completely redox only. It is completely redox. He's not asking us, I'm just telling you. So just see the trend. Acid base for NaCl and H2SO4, acid base. NaBr and H2SO4, somewhat acid base and redox. For NaI and H2SO4, completely redox. So do remember that trend too. It's very important. Now what's explanation of this for this part? We're studying for explanation for this part only. What's explanation? Explanation is down the group, the reducing power of halide ion increases. So Br minus in here, Br minus is stronger reducing agent than Cl minus, so it would be easily oxidized by H2SO4, would more easily oxidized to Br2 by H2SO4. Do you remember that, right? Cl minus from here cannot be oxidized by H2SO4, but Br minus can be oxidized by H2SO4 to form Br2. Okay, and itself this reducing agent gets oxidized, right? Okay, next part. Explain the differences. Okay, so let me read the question. Bunsen burner, we are heating these compounds. HCl does not decompose, where HI decomposes to form H2 and I2. What is the device this? Why is these observation different? Because obviously HCl bond is stronger than HI bond is stronger than HI bond. What does this mean? We need more energy to break HCl bond, or it doesn't get broken easily, stronger than HI bond, right? Down the group, the strength of the HI bond decreases. Why? Because the size of halogen gets bigger, bond length increase. Bond length is inversely proportional to the bond strength, so bond strength decreases down the group. So do remember, there's only 1 mark. That statement is more than enough, right? Next part. What is meant by strong bronzed lauric acid? Okay, so hardened halide dissolved water forms strong bronzed lauric acids. Okay, the concentration of the strong acid can be determined by titration. Okay, so what is meant by bronzed lauric acid? Okay, look, give the answer here in 2 steps. What's an acid and what's a strong bronzed lauric acid? Okay, don't take a risk. Take 2 separate marks. Okay, so you're gonna write what is an acid is a proton donor, and you get 1 mark for that. Okay, it means, what is meant by strong bronzed lauric acid? It means an acid is proton donor. It means an acid is proton donor, and look, by strong, it means that the acid completely dissociates when in solution, right? Okay, next part. This is again new syllabus 2022 pH titration curves. Okay, so you'll get a very good concept from this question, right? Okay, so on figure 3.2, sketch the pH titration curves produced when NaOH is added to 25 cm cube of HBr in excess. Okay, and 0.1 mole per dm cube of NH3 is added to HBr. Okay, so first concept, without drawing anything, this graph is for NaOH and HBr, this graph is for NH3 and HBr, right? So guys, look, very important, that is that what is NaOH? And we learned in IGCSE, NaOH is a strong base, right? Strong base. What is NH3? NH3 is a weak base. And what is HBr? it is a strong acid. HBr is just like HCl, strong acid. So this curve, this first curve is for what? Is for a strong, it is for a strong base and a strong acid, NH and NaOH and HBr, right? So if we have with adding, look, we are adding NaOH to HBr. So initial starting pH of that strong acid HBr is somewhere here, maybe 1, right? And the equivalence point, the vertical section of this pH titration curve will occur between pH 3 and at 25 cm3. At 25 cm3, the vertical section will occur maybe somewhere like here, right? Right. And the vertical section, we have got to remember these values, that vertical section of a strong base and strong acid is from pH 3 to pH 11, right? The vertical section of the graph. Okay, so then here is 11, and then the graph will just be like that. Okay, so let me just draw it. It will be something like this, and then a vertical section of the graph, and then it will be like that. Okay, that's how you draw the graph for a strong acid and a strong base. Equivalence point somewhere, you don't need to label it, and the graph is more than enough. Okay, do remember the vertical section occurs in this period for the strong acid, strong base titration. Next part is a weak base and a strong acid, right? Now we have the, we're adding the base, the ammonia NH3 into the strong acid. So again, starting pH would be the same, which is about 1. Titration, the equivalence point, the equivalence point, the neutralization point occurs at pH, occurs at a volume of 25 NH3, right? 25 volume of ammonia. And the vertical section for the titration pH, for the titration curve of the NH3, a weak base and a strong acid occurs between the pH what? pH 3 to pH almost about 7. So about starting from the same point, the vertical section of the graph, and going about to pH about almost like that, right? Okay. Now let me just draw that, and then it will go like a bit beyond here. You can also draw. Okay, so I think this is fine. So let me just draw it like that, and like this, a vertical section of the graph, right? You can draw it till 8 or 9, doesn't matter actually much. Then it's like that. No, actually this is not nice. This is, I think it, yeah, it is 9, sorry. I'm sorry, it is 9, right? Yeah. So this is the vertical section of the graph, and then it should not go beyond 12, right? It should not go beyond 12. Because why? This has gone till 14, I think, right? Almost 13, right? Okay. So this should not go beyond till, why? Because ammonia is a weak base, right? It should only about 10, 11, not more than that, right? So do remember, for the weak base and strong acid, the vertical section of the graph occurs between pH what? pH 3 to pH 9. This was pH 3 to pH 11. The vertical section has reduced, right? Because we're using a weak base. And also do remember this point, that this is not more than 12, 11. This has gone more than 14, right? More than 14, more than 13, right? Okay, so this is done here. Do remember how to do that. These might come in the Medium series, so this is very important concepts, right? Okay, next part. HBr reacts with propane to form 2 bromoalkanes. Okay, is given as the bromoalkanes. This is electrophilic addition reaction. Complete a diagram to show the mechanism of the reaction of HBr and propane to form the major product of the reaction. So guys, let's ask ourselves, which one of these will be the major product of the reaction? Obviously this one. Why? Because this is a secondary halogenoalkane. This is secondary. This is secondary halogenoalkane. This secondary halogenoalkane. This is primary. This is primary, right? So I'll draw the mechanism, and then you can see. I'll explain it to you in detail. This is important. Okay. So first of all, this is 1 mark minus, because bromine is more electronegative than hydrogen, right? So it takes electron density towards itself from the bond. Now this double bond attacks the positive part of the reagent, right? And then a carbon single bond is formed, the double bond is broken. Here is a CH3, here's a hydrogen, and hydrogen. I'll just do the structure. Now do remember, the Marconi curves will apply here. A hydrogen will be added to this carbon atom. and negative part will be with this carbon atom, because we learned that the negative part of the reagent attacks that carbon atom that has lesser number of hydrogens. This is the carbocation, right? So a bromine is the electrophile, it will, so the nucleophile, it will be attacking this way, right? So the negative part of the reagent attacks that carbon atom that has less number of hydrogen. This carbon has one hydrogen, this carbon has two hydrogens. So the hydrogen, the positive part of the attacking ingredient went to that carbon atom that had more hydrogens. So do you remember that concept? Now the product formation, it will be an H carbon carbon, and the CH3 and the bromine will be here. This is a secondary carbocation, and the three H's are here as per their word, right? One hydrogen got added to this carbon atom because it has more number of hydrogens. Marconi-Cove's rules apply here. Now, why the two bromoalkanes are not produced in the equal amounts? Very easy question. Because formation of major products, we're going to write formation of major product involves the production, major product involves production of secondary carbocation, production of 2 degree, or you can write secondary carbocation, which is more stable than the primary carbocation involved in the minor product of that carbocation, which is more stable than primary carbocation, more stable than primary carbocation. Why it is more stable? You got to put the reason. The question is about explaining. So you're going to write due to increased positive inductive effect, or you can write electron donating effect due to increased increased positive inductive effect of the two alkyl groups. Positive inductive effect of two alkyl groups, right? Like in this case, there's only one alkyl group on the carbon atom that is bonded to the halogen. And here there are two, right? So this is one, and this whole is one, right? More stable, right? So more stable, so that's why increased positive inductive effect of two alkyl groups. And then the part 3 says the reaction of CH3 CH2 Br and NaOH is different depending on whether the water or ethanol is used as a solvent. Complete the table 3.2 to identify the organic and inorganic products of the reaction of this 1 bromo propane with NaOH in each solvent. Okay. We're adding NaOH to the 1 bromo propane, and the solvent we're using is either water or ethanol. Whenever we're using water, the organic product is gonna be the alcohol, the corresponding alcohol, CH2CH2OH, nucleophilic substitution reaction. Instead of that, Br and OH comes there, and the inorganic product is this Na reacts with the Br, NaBr, easy. With ethanol, it is what? It is a elimination reaction. We're removing the HBr, right? Sorry, we're not removing HBr. Let me just tell you what are we doing. Yeah, we are removing HBr actually. The CH alkene would form CH3 and then CH and a CH2, right? So what got eliminated from here is what? It's hydrogen from this and Br from this, right? A hydrogen from this and Br from this. Br will react with Na to form NaBr as it was formed before too. Now the OH of this will react with the hydrogen eliminated from here, right? Eliminated from here. So forming water. So you got to know how this is 2 marks. This is tricky. Let me just draw it for you. So CH3, it is like that. C1 bromo alkane, bromine will be here. The dash, these are all hydrogens, right? We all know that. Hydrogens. Let me draw the bromine here for better concept. You can draw it anywhere. So these two will be eliminated to form, these two will be removed, okay, eliminated, and a double bond will form here, and then this will react with Na and this will react with OH of the NaOH, right, of the NaOH, forming water, and from here it will form NaBr. Okay, so we're gonna write all the organic products. If you write NaBr, don't write water, you won't get the mark, so be careful on that, right? I've also told you the type of reaction that is taking place, okay, and this is elimination reaction. Okay, next part. I think this should be the last question, right? Yeah, it is the last question. Words 15 marks. We should be done with this within 10 minutes. Compounds J and K are found in oils are found in plant oils, right? Complete table 4.1 to state what would you observe. What would you observe when J reacts with the reagents listed? Okay, so J. Let's analyze this compound. So an hydroxy group, third means it's an alcohol, and it is a tertiary alcohol. The atom that is bonded to carbon atom that is bonded to the OH group is bonded to three other carbon atoms. Tertiary alcohol. Do you remember that, right? And it has a CHO group, aldehyde, and it is also a ketone. This carbon, which is double bonded to an oxygen, is bonded to two carbon atoms. So this is also a ketone. So with 2,4-D and pH, it will form a yellow-orange PPT, precipitate. Look, remember that 2,4-D and pH reacts is a test used for carbonyl compounds. It can detect the CHO aldehyde group and the ketone group, right? Ketone group. It can also detect the ketone group. Do you remember that? This is the test that we use 2,4-D and pH. Now, specific test for aldehydes, not this tolerance reagent. This is the test for the aldehydes only. If the aldehyde group is present, it will be positive. Positive tolerance reagent test gives us observation of formation of silver mirror. Remember, this is very important. Silver mirror forms. Sodium metal will react with this OH, okay, and effervescence or fizzing of hydrogen gas will be observed. Effervescence will be observed. Okay, so do remember that sodium metal reacts with the OH. CHO, tolerance reagent for aldehydes. It is used for the aldehydes. Used to test the presence of aldehydes, right? Not the ketones. And positive test indicates this, right? Do remember everything. This is easy. J has two optical isomers. Three-dimensional structures. Whenever it says three-dimensional, mostly it's about the optical isomerism, right? The chiral centered thingy. Two optical isomers. Okay, J. Where is J? Oh yeah, we just analyzed. This is the chiral center. This OH bonded C, right? It's the chiral center. So we're going to be drawing the 3D dimensional structure with the chiral center, right? So there's a carbon atom, and from the top it's joined with the OH down. So 3D structure, we draw a wedge with a CH3, and then it's bonded to what? This group. It is COCH3, right? COCH3. COCH3, right? And this you can draw a dotted line too. What is on there here? It is CHO. Now on the other side, draw the exact mirror copy of that. COH, another wedge, again CH3. Now on this side, COCH3, and towards the mirror again CHO. This is 3D structure. This is mirror image. The mirror images are non-superimposable, having a chiral center there. Chiral center refers to a carbon atom that is bonded to 4 different types of groups. So that's how you are going to draw the 3 dimensional of the optical isomerism. Okay, I hope this is clear. This is easy, not hard at all. Next part. K is used to make addition polymer perpex. Okay, they put a trademark sign, right? As the synthesis of perpex is shown in the figure 4.2. Okay, this is how we're forming the perpex. We're using K to form M, and then reaction 2 we form the perpex. Identify L and the conditions required for the reaction 1. So this is the reaction 1 and this is the condition L. So look, everything remains the same in M, right? Everything is the same as in K, but the difference is here. This was a carboxylic acid. This is an ester, and formed by this was a Cu group. Okay, so now there are 2 carbon atoms, addition of 1 carbon atom, which means this is an acid. We're adding 1 carbon alcohol. What's that? It's methanol. We're adding methanol. The reagent L is methanol. Condition, now this is an esterification reaction. We're forming from carboxylic acid. By addition of alcohol, we are forming an ester. Water is eliminated. The condition for the reaction is heat under reflux, and we need H2SO4 catalyst. H2SO4 concentrated, full concentrated catalyst. Okay, so you know how to do that. To remember these values. So this esterification, try to understand it. It's one carbon alcohol, and this is the Cu group. This is the ester link COH, and this is the bond here with this carbon atom, right? So, and then it is joined to a CH3. right? CH3. So we've added another carbon atom. From where did the carbon atom came from? From one carbon alcohol. This is esterification. That is methanol. That is reagent L, reactant L. So do remember how do we do the COO is the ester linkage. We're forming esterification. Ester by esterification reaction, elimination of water. These are the conditions needed for the reaction. Draw one repeat unit of the polymer vertex. Okay, so we're just going to break the double bond here and join the continuous bond on both sides of the double bonded carbon atoms. Very easy, right? So like just notice this is the carbon, the center carbon atom. In between them there was a double bond, right? Just remove the double bond, keep all the atoms as they were, right? CH3, and there was this guy. It is COOCH3, right? This is only one repeat unit, right? And anything can be here, millions of molecules or whatever. This is a repeat unit, right? Millions of molecules can be there. We don't care. This is one repeat unit of the polymer perspex. This is done here. You're just gonna do what is the remove the double bond and add these two lines. These lines indicate that there can be a million, billions of these perplex molecules, right? This is the repeat unit, meaning that polymer, this is the repeat unit, this is the repeat unit, one more will be here, one more will be here, exact the same thing. So we have to draw the repeat unit. So do remember how to do that. Use information in the table 4.2 like this. Look, they won't give data booklet, you will be given with the information data you need for the question. So suggest question, right? How the infrared spectrum of M and perpex would differ. M and with M. Very easy. M has carbon-carbon double bond and this perpex has no carbon-carbon double bond. With carbon-carbon double bond, this alkene, this is the range. So we're going to write what is spectrum. We're going to write what is the spectrum of perspex have will have no carbon-carbon double bond peak at 1500 to 1680 per centimeter wavelength, right? So remember that. Easy, right? Very easy. There's no carbon-carbon double bond in purpose. Can you see the carbon-carbon double bond? It is not there. It's a polymer. And there's a carbon-carbon double bond in the M's, right? This is the difference in the infrared spectra. Now K, this is K, can be made from propanone, a ketone, by 3-step synthesis. Okay. Complete table 4.3 to identify the reagents used and the type of reaction in each step. This is step 1 of converting propanone to this hydroxynitrile, and then everything remained the same as it was in the hydroxynitrile. The only thing changed is the CN has changed to a Q group, acidic hydrolysis. And then what we did is we have removed the water, we have removed the OH group. So this is dehydration. The step 3 is dehydration, right? So this suppose step 1. Step 1 is the reagent we need is HCN and KCN as catalyst, and KCN as catalyst, right? And this is what reaction nucleophilic addition. You can just write addition, you will get the mark. If you want to write specifically, it's nucleophilic addition reaction. The propanone reacts with KCN and HCN to form this hydroxynitrile in the step 1. Now step 2. Everything remains the same. The only CN changes to a Q group. This is acidic hydrolysis. You got to write the full term, acidic hydrolysis. You have two choices here. You can use H2SO4 aqueous or you can use HCl aqueous. You can write, we have to write aqueous, it's important. Or you can write H positive aqueous, H2SO4 aqueous, all are fine. Step 3, Al2O3. In the alcohol, Al2O3 is a dehydrating agent, right? So the reaction is dehydration. Dehydration of alcohol produces alkenes, and this is an alkene. The K is an alkene, right? Everything has remained the same as it was here. The OH group is not there. It's a dehydration reaction. This is a dehydrating agent, a typical dehydrating agent. So I hope you get the point. What is happening? This is worth 5 marks and you got a score full marks. This is easy marks, not hard at all. So yeah, this is 15 marks. Yeah, so like look, important values, constant standards is given to you here. Avogadro's constant is important and specific capacity is used in Q is equal to MC delta T, right? And what else do you need? Yeah, this is molar gas constant. This is used in what? The equation, the general gas equation, which is PV is equal to nRT. This is the R 8.31. So like everything will be given to you in the exam, and there's a periodic table, like whatever that was in the data booklet. Now they have attached it at the end of the exam paper, right? So you can use it from there. Okay, so guys, this is the end of the exam, and this is completely solved in detailed solution. Okay, so this is February, March 2022, paper 2 2, and this is completely solved. And have a nice day. Thank you.